Tonight, we're going to explore one of the most sobering realities of space travel: the journey beyond our galaxy. We've sent spacecraft to every planet in our solar system. We've landed on Mars, explored Saturn's rings, touched the surface of a comet. Technology advances every year. Rockets get faster, more efficient, more capable. So naturally, we start wondering about the next frontier. Not just the next planet or the next star, but the next galaxy entirely. If we launched today with our fastest technology, pointed straight up out of the galactic disk and never stopped accelerating, when would we finally cross the boundary into intergalactic space? By the end of tonight, you're going to see exactly what that timescale looks like, and why the answer challenges every assumption we make about reaching the stars. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. The question seems straightforward enough. If we built the best spacecraft we could possibly imagine, loaded it with supplies, pointed it away from the galactic center, and launched it at maximum speed, how long would it take to leave the Milky Way entirely? To reach intergalactic space where no stars from our galaxy surround us anymore, where we're truly outside, looking back at the galaxy from the void beyond? The answer is going to surprise you. Not because it's complicated, but because it's so staggeringly long that it challenges our ability to comprehend time itself. But before we can calculate travel times, we need to understand what we're actually trying to escape from. What is the Milky Way? And more importantly, where does it end? The Milky Way is a barred spiral galaxy. From our perspective, inside it, we see a band of light stretching across the night sky. That band is our view of the galactic disk, a flat structure about 1,000 light-years thick and roughly 100,000 light-years in diameter. That's the main visible structure. The spiral arms, the bright stars, most of the gas and dust, all contained in this disk. But the galaxy doesn't stop there. Surrounding the disk is something called the halo, a roughly spherical region containing old stars, globular clusters, and most importantly, dark matter. The halo extends much farther than the disk. Depending on how you define the edge, the Milky Way's dark matter halo might extend 600,000 light-years from the center, maybe even farther. Some estimates push it to nearly 1,000,000 light-years. That's the real size of our galaxy. Not the 100,000 light-year disk you see in pretty pictures, but a massive dark matter structure 10 times larger. And here's the critical point for our escape attempt. As long as you're inside the dark matter halo, you're still gravitationally bound to the galaxy. You haven't escaped. You're still orbiting the galactic center, still part of the system. True escape means getting beyond the point where the Milky Way's gravity has any meaningful hold on you. The disk itself is where most of the action happens. This is where you find the spiral arms, those beautiful sweeping structures you see in photographs of the Milky Way. The spiral arms aren't solid structures. They're density waves, regions where stars and gas clouds bunch together as they orbit. Think of them like traffic jams on a highway. The cars, or in this case stars, move through the jam. But the jam itself stays in the same place. The spiral arms are where most star formation occurs. Gas clouds moving through the spiral arms get compressed, and that compression triggers gravitational collapse, leading to new stars. The brightest, hottest, most massive stars live only a few million years before exploding as supernovae, so they never travel far from where they were born. That's why spiral arms are so bright and blue. They're filled with these young, hot, massive stars. Between the spiral arms, the disk is quieter. There are still plenty of stars, but they're older, cooler, and more spread out. The Sun sits in one of these inter-arm regions, in what's called the Orion Spur. We're not in a major spiral arm. We're in a minor structure between the Perseus arm and the Sagittarius arm. This is probably fortunate. The spiral arms are more chaotic, with more supernovae, more radiation, more gravitational perturbations. Our quiet location between arms may have been crucial for life's development on Earth. The galactic center is a very different environment. It's incredibly dense, packed with stars. If you could somehow transport Earth to a location 1,000 light-years from the galactic center, the night sky would be filled with millions of stars, bright enough to cast shadows. There would be no darkness, just a permanent twilight from the combined glow of all those nearby stars. At the very center sits Sagittarius A, a supermassive black hole weighing about 4 million times what the Sun weighs. It's surrounded by a dense cluster of stars orbiting at incredible speeds. Some of these stars complete orbits in just 15 to 20 years, which is astonishing when you realize they're traveling at thousands of miles per second. The galactic center is also a source of intense radiation. X-rays, gamma rays, cosmic rays, all streaming out from the region around Sagittarius A. Any planet in that region would be bathed in radiation levels far higher than what we experience here in the Orion Spur. Life as we know it would struggle to survive there. The halo is stranger still. It contains very old stars, some of the oldest in the galaxy, dating back nearly to the Big Bang itself. These stars formed in the early universe when there were almost no heavy elements. They're made almost entirely of hydrogen and helium. They're called population 2 stars, to distinguish them from younger population 1 stars like the Sun that have significant amounts of heavier elements. Some of these old stars are gathered into globular clusters, tight, spherical collections of hundreds of thousands or even millions of stars. The Milky Way has about 150 known globular clusters, scattered through the halo like satellites orbiting the main galaxy. Each globular cluster is ancient, typically 10 to 13 billion years old. Their stars are all roughly the same age, having formed together in a single burst of star formation early in the galaxy's history. Globular clusters are beautiful objects. Through a telescope, they look like spherical swarms of stars, dense in the center and gradually thinning out toward the edges. But most of the halo's mass isn't in stars at all. It's in dark matter. We can't see dark matter directly, but we can detect its gravitational effects. When astronomers measure how fast stars orbit the galaxy at different distances from the center, they find that the speeds don't match what we'd expect based on the visible matter alone. Stars, far from the center, out in the halo, are orbiting much faster than they should be if gravity came only from the stars and gas we can see. The only explanation that fits the observations is that there's additional mass we can't see, distributed throughout the halo. This is dark matter. It doesn't emit light, doesn't absorb light, doesn't interact with electromagnetic radiation at all. It only interacts through gravity, and there's a lot of it. The Milky Way's dark matter halo contains roughly 10 times as much mass as all the stars, gas, and dust in the galaxy combined. Most of the galaxy's mass is invisible. For our escape attempt, this matters enormously. The dark matter's gravity is what extends the galaxy's influence so far out. Without dark matter, the galaxy would be much smaller, and escaping would be correspondingly easier. But with dark matter, the gravitational pull extends hundreds of thousands of light years. That's what we have to overcome. Let's establish where we're starting from. Earth orbits the Sun at a distance of about 93 million miles. The Sun itself sits about 26,000 light-years from the galactic center. We're in a relatively calm region between spiral arms, a spot sometimes called the Orion Spur or the local arm. The Sun orbits the galactic center at roughly 140 miles per second. That's around 500,000 miles per hour. Incredibly fast by everyday standards. You could circle Earth's equator in less than 5 minutes at that speed. But on galactic scales, it's leisurely. At this speed, the Sun takes approximately 225 million years to complete one orbit around the galaxy. The last time we were at this exact point in the galaxy, dinosaurs were just beginning to dominate Earth. The next time we return to this spot, who knows what Earth will look like. So we're moving, constantly, sweeping through space on this slow galactic orbit. But orbital motion doesn't help us escape. It just keeps us circling. To actually leave, we need to add velocity. We need to accelerate away from the galactic center, faster than the galaxy's gravity can pull us back. This brings us to the concept of escape velocity. You might be familiar with escape velocity from Earth. To leave Earth's gravitational pull entirely, you need to reach about 25,000 miles per hour or 7 miles per second. Launch a rocket slower than that, and it will eventually fall back. Launch it faster, and it will escape into space. The same principle applies to escaping the Milky Way. There's a speed you need to reach, relative to the galactic center, to break free from its gravitational grip. But calculating that speed is complicated. Earth is a simple case because you're escaping from a single concentrated mass. The Milky Way is different. The mass is distributed throughout the galaxy. There's the central bulge containing billions of stars. There's the disk with its spiral arms. There's the halo, filled with dark matter. All of this mass contributes to the gravitational field, and the strength of that field changes depending on where you are. Near the center, the pull is strongest. Far out in the halo, it's weaker. And unlike Earth's gravity, which falls off smoothly as you move away, the galaxy's gravitational field has a more complex structure because you're inside a distributed mass rather than outside a point mass. Despite these complications, we can estimate the escape velocity from our current location. From where the Sun sits, about 26,000 light-years from the center, the escape velocity is roughly 340 miles per second. That's around 1.2 million miles per hour. Remember, we're already moving at 140 miles per second in our orbital motion. But that motion is sideways, carrying us around the galaxy, not away from it. To escape, we need to add velocity in the outward direction. And we need to add enough to reach 340 miles per second relative to the galactic center. That's the baseline speed we need to actually break free and coast into intergalactic space. Anything slower, and we'll eventually be pulled back, our outward motion reversed by gravity, drawn back into an orbit. Now let's talk about spacecraft. What can we actually build, and how fast can we make it go? The fastest spacecraft humans have ever built is the Parker Solar Probe, launched in 2018 to study the Sun. At its closest approach to the Sun, using gravitational assists and its highly elliptical orbit, the Parker Solar Probe reaches speeds of about 430,000 miles per hour. That's roughly 119 miles per second. Astonishingly fast. The probe is moving so quickly that it could travel from Los Angeles to New York in less than 8 seconds. But even at that incredible speed, it's still nowhere near galactic escape velocity. We're moving at 119 miles per second. We need to reach 340 miles per second. And remember, the Parker Solar Probe achieves its speed by falling toward the Sun and using careful gravitational assists. It's not carrying enough fuel to reach that speed through thrust alone. In deep space, far from any massive object to slingshot around, we couldn't use the same tricks. Let's imagine we built a similar probe, specifically designed to leave the galaxy. We give it the best chemical rocket engines we have. We optimize everything for maximum speed. Even in the most optimistic scenario, chemical rockets are limited by the energy density of their fuel. The exhaust velocity of chemical rockets tops out around 9 to 10,000 miles per hour. This is a fundamental limit based on the chemistry involved, the energy released when hydrogen and oxygen combine, or when other chemical fuels burn. You can't push beyond this without changing the fundamental propulsion method. And because of something called the rocket equation, which relates the mass of fuel to the mass of the spacecraft and the exhaust velocity, reaching high speeds with chemical rockets requires carrying enormous amounts of fuel. To reach even a fraction of galactic escape velocity using chemical rockets would require a spacecraft that's almost entirely fuel with just a tiny payload. And even then, you wouldn't get close to the speeds we need. So, chemical rockets are out. What about more advanced propulsion? Nuclear rockets use nuclear reactions instead of chemical ones. Instead of burning chemical fuel, you heat a propellant, typically hydrogen, with a nuclear reactor and expel it through a nozzle. The exhaust velocity can be higher, maybe 30,000 to 60,000 miles per hour, depending on the design. Better than chemical rockets, but still not enough. Even with nuclear propulsion, reaching 1.2 million miles per hour would require carrying absurd amounts of fuel. The specific impulse, a measure of rocket efficiency, is better than chemical rockets, but not enough better to solve the fundamental problem. Nuclear thermal rockets were actually developed and tested in the 1960s and 70s under Project Nerva. The tests showed the concept worked. They successfully demonstrated nuclear reactors that could heat hydrogen to extreme temperatures and produce thrust. But the program was cancelled, partly because of concerns about launching nuclear material into space, partly because of budget cuts. Still, the technology is proven. We could build a nuclear rocket if we decided to. It would be better than chemical rockets for deep space missions, with higher efficiency and greater total velocity capability. But it's still nowhere near what we need for galactic escape. What about ion drives? These are electric propulsion systems that use electricity to accelerate ions to very high speeds and expel them as exhaust. The exhaust velocity is much higher than chemical rockets, sometimes reaching 30 to 60 miles per second. That's excellent. The problem is thrust. Ion drives produce very low thrust because they're expelling very small amounts of mass, even though they're expelling it at high speed. The Dawn spacecraft, which visited the asteroids Vesta and Ceres, used an ion drive. Its thrust was about 90 millinewtons. To put that in perspective, that's roughly the weight of a piece of paper pressing on your hand. With such low thrust, acceleration is extremely slow. Dawn took 4 years to travel from Earth to Vesta. For escaping the galaxy, ion drives face a fundamental problem. They need electricity to operate, and that electricity has to come from somewhere. Dawn used solar panels, but as you travel farther from the sun, solar panels become less effective. The intensity of sunlight drops with the square of the distance. At Jupiter's distance, solar panels receive only about 4% of the sunlight they'd receive near Earth. Beyond Saturn, solar power becomes impractical. You'd need a different power source. Nuclear power is an option. A radioisotope thermoelectric generator, or RTG, uses the heat from radioactive decay to generate electricity. Voyager and Cassini used RTGs. They work well for powering instruments, but they don't produce enough power for high-thrust propulsion. You'd need a nuclear reactor, something much more complex and massive. Even with a reactor, the power output limits how much acceleration you can achieve. And ion drives still can't reach the speeds we need. They're great for missions within the solar system, where you have years or decades to accelerate. For escaping the galaxy, they don't help much. What about nuclear pulse propulsion? This is a concept, never actually built, where you detonate nuclear bombs behind your spacecraft and ride the shockwave. It sounds insane, and it is, but it's based on real physics. A design called Project Orion was studied in the 1950s and 60s. The idea is simple in concept. You carry a supply of nuclear devices, maybe thousands of them. You eject one behind the spacecraft, detonate it, and the explosion creates a cloud of plasma expanding in all directions. Some of that plasma hits a pusher plate on the back of your spacecraft. The pusher plate is connected to the rest of the spacecraft through shock absorbers. The impact transfers momentum, accelerating the spacecraft. Then you repeat. Eject another bomb, detonate it, absorb the blast, accelerate. Over and over, thousands of times. With each blast, you add more velocity. The calculations showed this could work. You could accelerate to significant fractions of light speed, perhaps 5 or 10%. The pusher plate would need to be incredibly robust, made of something that could withstand repeated nuclear blasts without ablating away. The shock absorbers would need to smooth out the impulses so the spacecraft doesn't get torn apart. And you'd need to solve the problem of launching such a craft from Earth without irradiating the planet. Most designs assumed you'd assemble it in orbit and start the pulse propulsion only after you were well away from Earth. The engineering challenges are enormous. You're setting off nuclear explosions directly behind your spacecraft. The structure needs to withstand repeated nuclear blasts without breaking apart. You need shock absorbers that can handle the impulse from each detonation. Each blast would be like getting hit by a massive hammer. The forces would be incredible. You need to carry hundreds or thousands of nuclear devices. Each one adds weight, which reduces your final velocity according to the rocket equation. There's a trade-off between carrying enough bombs to reach high speed and not carrying so many that the added weight defeats the purpose. The political and environmental issues of launching such a craft from Earth are probably insurmountable. International treaties ban nuclear weapons in space. Public opposition to launching thousands of nuclear devices would be fierce. The risk of an accident during launch, scattering nuclear material across the atmosphere, would be unacceptable to most people. And even if you solved all of that, you still have the problem of where you're going. Nuclear pulse propulsion could theoretically get you to 10% of light speed. That's fast enough to reach nearby stars within a human lifetime. Alpha Centauri, at 10% light speed, is about a 42-year journey. But for escaping the galaxy, even 10% of light speed isn't fast enough. The journey still takes millions of years. What about fusion rockets? Nuclear fusion, the process that powers the sun, releases more energy per unit mass than fission. If you could build a rocket engine that uses fusion reactions to heat and expel propellant, you could achieve very high exhaust velocities. Theoretical designs suggest exhaust velocities of 1% to 10% of light speed might be possible. That would be revolutionary. With exhaust velocity that high, the rocket equation becomes much more favorable. You could reach significant fractions of light speed without needing impossible mass ratios. But fusion propulsion faces a fundamental problem. We haven't figured out how to make fusion work as a practical energy source, period. Fusion research has been ongoing for over 60 years. The goal is to create a reactor that produces more energy than it consumes. This is called break-even. We've gotten close. Recent experiments at the National Ignition Facility achieved fusion break-even in late 2022. They used powerful lasers to compress a tiny pellet of fusion fuel, triggering a fusion reaction that released more energy than the lasers delivered to the pellet. But the total energy consumed by the facility, including the energy to power the lasers and all the support systems, was far greater than the energy released by fusion. So, it's a step forward. But we're still far from a practical fusion reactor. And even if we had a working fusion reactor for power generation, adapting it to propulsion is another challenge entirely. A power plant can be massive and stationary. A rocket engine needs to be compact, lightweight, and able to operate continuously for years. The requirements are completely different. So fusion propulsion remains theoretical. It might be possible someday, but we're decades or centuries away from building one. What about antimatter? Antimatter is the most energy-dense fuel theoretically possible. When matter and antimatter meet, they annihilate completely, converting 100% of their mass into energy, according to Einstein's equation E equals mc squared. This is far more efficient than nuclear fusion, which converts less than 1% of mass into energy. For comparison, burning gasoline converts about 1/1000th of its mass into energy. Fission converts about 0.1% of mass to energy. Fusion converts less than 1%. Matter-antimatter annihilation converts 100%. Nothing in physics allows for a more efficient energy release. An antimatter rocket could theoretically reach significant fractions of light speed. Let's say we could build one that reaches 50% of light speed. The exhaust would be photons and other particles moving at or near light speed. The specific impulse would be the theoretical maximum allowed by physics. But here's the problem. We have no idea how to build an antimatter rocket. Antimatter exists. We've created tiny amounts in particle accelerators, but it's phenomenally difficult to produce and store. Creating antimatter requires enormous amounts of energy. You need to collide particles at very high energies, creating particle-antiparticle pairs. The LHC at CERN can produce antimatter, but only tiny amounts. A few nanograms per year. To give you a sense of scale, a nanogram is 1/1000th of a gram. Creating a single gram of antimatter would require more energy than humanity produces in a year. Current estimates suggest producing 1 gram of antiprotons would cost about $60 trillion with current technology. And you'd need tons of antimatter to fuel a spacecraft on an interstellar mission. Storing it is another nightmare. Antimatter annihilates instantly upon contact with normal matter. If even a single antimatter atom touches the container, it explodes. You can't use normal containers. The only way to store antimatter is with magnetic containment. You suspend the antimatter particles in a vacuum using powerful magnetic fields, keeping them away from the container walls. This works in particle physics labs for very small amounts stored for very short times. Scaling it up to store tons of antimatter for years or centuries is another matter entirely. The magnetic containment system would need to operate perfectly for the entire mission duration. Any failure, any power loss, any glitch, and the antimatter touches the container and releases energy equivalent to multiple nuclear weapons. Your spacecraft vaporizes. So, while antimatter propulsion is theoretically possible, it's so far beyond our current capabilities that we might as well be talking about magic. We can write down the equations. We can show it doesn't violate any known laws of physics. But building it is another question entirely. Let's say we did it. Let's say we built a nuclear pulse spacecraft capable of reaching 10% of light speed, and we pointed it straight up out of the galactic disk. Let's calculate how long it would take to truly escape the Milky Way. First, we have the disk itself. The disk is about 1,000 light-years thick. At 10% of light speed, crossing the disk would take 10,000 years. 10,000 years just to get through the visible part of the galaxy. But we're not done. Beyond the disk is the halo, extending hundreds of thousands of light-years. If we're generous and say the halo extends to 300,000 light-years, and we're starting 26,000 light-years from the center, we need to travel outward until we're 300,000 light-years from the center. That's 274,000 light-years of travel. At 10% of light speed, that's 2.74 million years. Nearly 3 million years. To put that in perspective, 3 million years ago, humans didn't exist. Our species, Homo sapiens, wouldn't evolve for another 2.7 million years. 3 million years ago, our distant ancestors were creatures like Australopithecus, walking upright, but with brains a third the size of ours, using the most primitive stone tools. 3 million years from now, if humans still exist in any recognizable form, we'd be so changed by evolution or technology that calling them human might be inaccurate. That's how long this journey would take, with our nuclear pulse spacecraft traveling at 10% of light speed. And that's assuming we can build such a craft, which we can't. Let's think more carefully about what this journey would actually entail. The spacecraft launches from near-Earth space. It begins its nuclear pulse sequence, detonating bombs and accelerating. The acceleration phase might last weeks or months, depending on how many bombs it carries and how frequently it detonates them. Each detonation provides an impulse, a sudden kick of velocity. String together thousands of these impulses, and you build up significant speed. Eventually, it exhausts its supply of bombs and reaches its cruising speed. Let's say 10% of light speed. Then it coasts. For millions of years, it just coasts through space. There's no more acceleration. The engines, if you can call a bomb detonation system an engine, are shut down permanently. The spacecraft is now a ballistic object, following a trajectory determined by its initial velocity and the gravitational fields it passes through. during the first few thousand years, it's still passing through the galactic disk. It might pass near other stars, coming within a few light years of them. From the spacecraft's perspective, stars would slowly drift past. Over decades, a star that was ahead would move to the side and then behind. Eventually, it would fade into the background. It might pass through molecular clouds, regions where new stars are forming. The density of matter in these clouds is still incredibly low by terrestrial standards. A typical molecular cloud has maybe 1 million hydrogen molecules per cubic centimeter. That sounds like a lot, but Earth's atmosphere at sea level has about 25 quintillion molecules per cubic centimeter. So, the molecular cloud is a vacuum by our standards. But at 10% of light speed, even this sparse gas becomes a hazard. The spacecraft is moving at roughly 18,600 miles per second. Any atom or dust grain it hits doesn't just bounce off. At these speeds, collisions are violent. A single hydrogen atom hitting the spacecraft carries kinetic energy. For one atom, that energy is tiny. But multiply it by 1 million atoms per cubic centimeter, and multiply that by the cross-sectional area of the spacecraft. And suddenly, you're talking about significant erosion over time. The spacecraft would need thick shielding on the front. Layers of material designed to ablate gradually under repeated impacts, protecting the more sensitive components behind. Even tiny dust grains, specks of material so small you couldn't see them with the naked eye, become destructive. A grain of sand, weighing maybe 1 milligram, hitting at 10% of light speed, would release energy equivalent to several kilograms of TNT exploding. It would punch through ordinary materials like they weren't there. This is why interstellar spacecraft designs often include Whipple shields, multiple layers of material spaced apart. The first layer breaks up incoming particles. The fragments spread out. The next layer catches the fragments, breaking them up further. By the time the debris reaches the inner layers, it's dispersed enough that it doesn't cause catastrophic damage. But even Whipple shields wear out. Over millions of years, countless impacts would erode the shielding, eventually compromising the spacecraft. As the spacecraft climbs out of the disk and into the halo, the density of matter decreases. The disk contains most of the galaxy's gas and dust. The halo is cleaner, filled mostly with old stars and dark matter. Collisions become less frequent. The erosion rate drops. But the spacecraft is already damaged by this point, scarred by millions of years passing through the disk. The halo is dark. There are stars, but they're much more spread out than in the disk. In the disk, near the Sun's location, the average distance between stars is about 5 light-years. In the halo, stars might be separated by hundreds or even thousands of light-years. If the spacecraft had functioning cameras, which it wouldn't after this long, the view would be striking. The galactic disk would be behind and below, appearing as a bright spiral structure. Ahead and around, just darkness dotted with occasional stars. Globular clusters would appear as fuzzy patches of light, concentrated swarms of stars. The spacecraft might pass through one of these clusters. Globular clusters are dense by astronomical standards. In the core of a globular cluster, stars might be separated by only 0.1 to 0.01 light-years. That's 6,000 to 60,000 astronomical units. Still vast distances, but much closer than the typical spacing between stars. Inside the cluster, the sky would be filled with stars. Thousands of stars visible to the naked eye if anyone were there to look, many bright enough to cast shadows. The combined light from all those stars would create a permanent twilight. True darkness would never fall, but there's no one there to see it. The spacecraft is automated, or more likely, dead. Electronic systems don't last millions of years. Consider what happens to electronics over long time periods. Radiation damage accumulates. Every time a cosmic ray, a high-energy particle from space, strikes a microchip, it can flip bits in memory, corrupt data, damage circuits. Most cosmic rays are protons or helium nuclei traveling at close to light speed. When they hit a semiconductor, they create cascades of electrons, disrupting normal operation. Modern spacecraft have radiation-hardened electronics designed to resist this. But even hardened electronics accumulate damage over time. Error-correcting codes can fix some problems. Redundant systems can compensate for failed components. But over centuries, over millennia, the damage becomes overwhelming. Components degrade through other mechanisms too. Solder joints develop micro-cracks from thermal cycling. As the spacecraft moves through regions of different temperature, materials expand and contract. Solder, the metal alloy that connects components to circuit boards, is particularly vulnerable. Tiny cracks form, grow, eventually break connections. Capacitors dry out. Electrolytic capacitors contain liquid electrolyte that slowly evaporates or breaks down chemically. After decades, they lose capacitance, eventually fail completely. Resistors drift from their nominal values. Mechanical stresses and temperature variations cause tiny changes in resistance. These changes accumulate. Micrometeorite impacts destroy sensitive equipment. Even in the halo where dust is sparse, over millions of years, some impacts are inevitable. A micrometeorite punching through the hull can destroy whatever it hits. Mechanical systems seize up. Lubricants break down chemically. Bearings that once spun smoothly become rough, eventually freeze completely. Motors fail. Valves stick. Solar panels, if the spacecraft has them, degrade from radiation exposure. The semiconductor materials that convert light to electricity get damaged by high-energy particles. Their efficiency drops year by year until they produce almost nothing. Nuclear power sources decay. An RTG, a radioisotope thermoelectric generator, might last a few decades, maybe a century if you're lucky. But the radioactive isotope is constantly decaying. The heat output drops. Eventually, there's not enough heat to generate usable electricity. A nuclear reactor might last longer, but reactors need maintenance. Fuel rods need replacement. Control systems need monitoring. Coolant loops need inspection. None of this happens on a dead spacecraft coasting through the void. Even if the spacecraft was designed with extraordinary redundancy, with hardened systems and hypothetical self-repair mechanisms, eventually everything fails. There's a concept in reliability engineering called the bathtub curve. Component failure rates are high, initially due to manufacturing defects, early failures, infant mortality. Then there's a long period of low, constant failure rate, normal operation. Then failure rates rise again as components wear out, reach end of life. For a spacecraft on a million-year journey, you're deep into the wear-out phase. Everything is failing. After a few thousand years, certainly after 10,000 years, the spacecraft is probably completely inert. Just a lump of metal and composite materials coasting through space on momentum. No power. No functioning systems. No ability to sense, record, or transmit anything. Just debris. And it keeps coasting. Through the halo. Past the globular clusters. Into the outer reaches, where even the halo's stars become sparse. The gravitational pull of the Milky Way slowly weakens as the spacecraft gets farther from the galactic center. Gravity follows an inverse square law. Double the distance, the force becomes 1/4 as strong. Triple the distance, 1/9 as strong. The Milky Way's gravity extends far, but it gets weaker and weaker with distance. At some point, the spacecraft crosses a threshold. It's no longer gravitationally bound to the galaxy. Its velocity exceeds the local escape velocity. Even if you stopped the spacecraft here and let it drift, gravity wouldn't pull it back. It would continue moving outward, just more slowly. But the spacecraft isn't drifting. It's still moving at 10% of light speed. It has more than enough velocity to escape. It crosses into intergalactic space. There's no sharp boundary, no sign marking the edge of the galaxy. But there's definitely a transition. The density of stars drops to nearly zero. The background gravitational field changes. The spacecraft is now in the void between galaxies. Looking back, if anyone could look, the Milky Way would appear as a bright spiral structure receding into the distance. The view would be spectacular. The entire galaxy visible at once, not the inside view we get from Earth, where we see the disk edge on as a band across the sky. From outside, you'd see the spiral arms, the central bulge, the graceful structure of the whole galaxy. And ahead, other galaxies. Andromeda, much closer now from this location than it appears from Earth. The Triangulum Galaxy, M33. Various dwarf galaxies scattered through the local group, but the spacecraft doesn't see any of this. Its cameras are dead, have been dead for millions of years. It's blind, deaf, powerless, just a piece of human-made debris coasting through the cosmos. And it keeps moving. There's no friction in space to slow it down. Newton's first law states that an object in motion stays in motion unless acted upon by an external force. In the near vacuum of intergalactic space, there are no significant external forces. The gravitational pull from the Milky Way is negligible at this distance, and falling behind, the pull from other galaxies is too weak and too distant to matter. The spacecraft maintains its velocity indefinitely. Barring a collision with something, which is spectacularly unlikely given how empty intergalactic space is, the spacecraft will maintain its 10% of light speed forever. Intergalactic space is even emptier than interstellar space. In the galactic disk, there might be 1 million hydrogen atoms per cubic meter. In intergalactic space, there might be 1 atom per cubic meter, 1 single atom per cubic meter on average. That's as close to a perfect vacuum as exists anywhere in the natural universe. The spacecraft will spend the rest of time, literally, moving through this void. It might, by chance, eventually pass near another galaxy. In a few tens of millions of years, if its trajectory happens to intersect one. But probably not. Galaxies occupy a tiny fraction of the universe's volume. If you randomly threw a dart at a map of the universe, the overwhelming odds are it would land in intergalactic space, not in a galaxy. Most of space is empty. The spacecraft will probably spend eternity in the gaps between galaxies, never coming close to any of them. And as time passes, billions of years, the universe around the spacecraft changes. The expansion of the universe carries galaxies farther apart. The local group, the Milky Way, and Andromeda, and their satellite galaxies, bound together by gravity, will merge. This process is already beginning. In about 4 billion years, Andromeda and the Milky Way will collide. Over the following few billion years, they'll merge completely into a single giant elliptical galaxy. The Triangulum Galaxy and the various dwarf galaxies will also merge into this structure. The result will be one large galaxy, sometimes playfully called Milkomeda. But everything beyond the local group will disappear. The expansion of the universe, driven by dark energy, accelerates over time. Galaxies outside the local group are already moving away from us. The farther they are, the faster they recede. Eventually, they'll cross the cosmic horizon, receding faster than light. Not moving through space faster than light, which would violate relativity, but being carried by the expansion of space itself. And once they cross that horizon, their light can never reach us again, no matter how long we wait. In 1 trillion years, the observable universe, as seen from the location of our spacecraft, will contain only the merged remnant of the local group. Everything else will have expanded away beyond the reach of observation. The cosmic microwave background, the afterglow of the Big Bang, will have redshifted into undetectability. The universe will appear dark except for the single merged galaxy, now very distant. And in quadrillions of years, even that single galaxy will fade. Stars will burn out. The universe will run out of hydrogen to make new stars. Existing stars will exhaust their fuel. The smallest red dwarfs, which can burn for trillions of years, will eventually sputter out. White dwarfs will cool into black dwarfs, dark remnants emitting no light. Neutron stars will remain dark and cold. Black holes will slowly evaporate through Hawking radiation, though this takes unimaginably long. A solar mass black hole takes about 10 to the power of 67 years to evaporate. That's 10 with 67 zeros after it. A number so large it's meaningless to human comprehension. Eventually, all the black holes evaporate. All the matter decays or disperses. The universe becomes a thin soup of photons and elementary particles, spreading through ever-expanding space. Temperature approaches absolute zero. Entropy maximizes. This is heat death, the ultimate fate of the universe, according to our current understanding. And through all of this, the spacecraft keeps moving, coasting through the void. Forever. This is the ultimate fate of anything that escapes the Milky Way. Not adventure, not discovery, not reaching some distant destination. Just an eternity of drifting through increasing darkness, isolation, and eventual emptiness. But let's get more realistic. Let's use the Parker Solar Probe speed, 119 miles per second, since that's something we've actually achieved. How long would escape take at that speed? First, convert our speeds to comparable units. 119 miles per second is about 0.0006, 4 times the speed of light. Not even 1/10 of 1% of light speed. If the halo extends to 300,000 light-years from the center, and we need to travel 274,000 light-years outward, at this speed, the journey would take roughly 428 million years. 428 million years. The last time that much time passed, vertebrates were first crawling onto land. Fish were evolving into amphibians. The supercontinent Pangaea wouldn't form for another 200 million years. Dinosaurs wouldn't appear for another 200 million years after that. And this is using our fastest spacecraft, the absolute pinnacle of current human technology. The numbers are so large, they become abstract. Let me try to make them more concrete. Imagine you launch this spacecraft today, right now, with the mission to escape the Milky Way. You'd need to build something that could function for 428 million years. No maintenance, no repairs, no software updates. It would need to survive countless impacts with interstellar dust and gas. It would need to operate through variations in temperature, radiation exposure, and the slow decay of its components. Nothing humans have ever built has lasted even 10,000 years while still functioning. The oldest existing structures on Earth, things like Stonehenge or the pyramids, are around 4,500 years old, and they're not functional machines, just piles of stone. The oldest operational machines are maybe a few hundred years old, clocks and simple mechanisms, and they've been maintained constantly. The idea of a spacecraft functioning for 428 million years is absurd. But even if we solve that impossible engineering challenge, there's another problem. Who's monitoring this mission? Humanity would need to maintain continuity of civilization for 428 million years. We'd need to pass down the mission across countless generations. We'd need to avoid extinction, avoid societal collapse, avoid losing the knowledge of why this spacecraft was launched in the first place. In 428 million years, humanity would likely evolve into something completely different, or go extinct, or spread to other stars and become a million different species, adapted to different worlds. The idea that anyone would still care about this mission after even a million years, let alone 428 million, is difficult to imagine. Here's another way to think about it. The Milky Way is about 13.6 billion years old. It formed not long after the Big Bang, when the universe was only a few 100 million years old. In the 13.6 billion years since then, the galaxy has rotated about 60 times. The Sun has only completed about 20 orbits since it formed 4.6 billion years ago. In the time it would take our spacecraft to escape the Milky Way, the Sun would complete nearly 2 more orbits. The galaxy would rotate nearly twice. Stars would be born and die. The Sun itself would expand into a red giant, engulf the inner planets, and then collapse into a white dwarf. All of that would happen before the spacecraft reached intergalactic space. Let's walk through what 428 million years actually means for Earth, the Sun, and life. Right now, the Sun is about 4.6 billion years old. It's a main sequence star, fusing hydrogen into helium in its core. This process will continue for another 5 billion years or so. But the Sun is gradually getting brighter. As helium builds up in the core contracts slightly and heats up. This makes the fusion reactions run faster. The Sun outputs more energy. Over its lifetime, the Sun has increased in luminosity by about 30%, and it will continue brightening. In about 1 billion years, the Sun will be bright enough that Earth's oceans start to evaporate. The water vapor creates a greenhouse effect. Temperatures soar. Eventually, all of Earth's water escapes into space. Earth becomes a dead, dry world, like Venus, but even hotter. This is Earth's fate in about 1 billion years. Our spacecraft, on its 428 million-year journey, would be less than halfway to escaping the galaxy when Earth becomes uninhabitable. Life on Earth would end. The biosphere would collapse. Every living thing would perish. And the spacecraft would keep coasting outward, indifferent, dead itself probably, just metal and composites moving through the void. In about 5 billion years, the Sun will exhaust the hydrogen in its core. Fusion will stop. The core will contract and heat up. A shell of hydrogen around the core will start fusing. The outer layers of the Sun will expand enormously. The Sun will become a red giant, swelling to perhaps 100 times its current diameter. It will engulf Mercury's orbit, probably Venus's orbit, possibly Earth's orbit, though Earth will have moved outward slightly due to mass loss from the Sun. Even if Earth isn't literally engulfed, it will be heated to thousands of degrees. Any remaining solid material will vaporize. The Sun will remain a red giant for a few 100 million years. Then it will shed its outer layers in a series of pulses. These layers will form a planetary nebula, a beautiful shell of glowing gas expanding into space. At the center will be the Sun's core, now exposed. A white dwarf, about the size of Earth, incredibly hot but gradually cooling. No longer fusing anything, just radiating away stored heat. This white dwarf will cool for billions of years, eventually becoming a black dwarf, a cold, dark remnant emitting almost no light. All of this, the Sun's entire remaining life cycle, happens in less time than our spacecraft needs to escape the galaxy. The spacecraft would outlive the Sun. The galaxy itself changes over 428 million years. New stars form. Old stars die. Supergiant stars, the most massive ones, live only a few million years before exploding as supernovae. In 428 million years, thousands of supernovae would occur in our galaxy, each one briefly outshining billions of normal stars, each one scattering heavy elements into space, enriching the interstellar medium, providing material for future generations of stars and planets. Some stars would form, live their entire lives, and die while the spacecraft is in transit. The spiral arms would shift. The spiral arms aren't rigid structures. They're density waves, rotating at a different speed than the stars. Stars move through the spiral arms, spend some time in the dense regions, then move back out. Over 428 million years, the pattern of spiral arms would change substantially. The Milky Way would still be recognizable, but the details would be different. And there's the ongoing collision with smaller galaxies. The Milky Way is consuming several dwarf galaxies right now. The Sagittarius dwarf elliptical galaxy is being torn apart by tidal forces. Its stars are being scattered and absorbed into the Milky Way. This process will continue. Over 428 million years, these dwarf galaxies will be fully assimilated. Their stars will become part of the Milky Way's halo. All of this is just the prologue to the larger collision with Andromeda, which happens in about 4 billion years. Our spacecraft escapes before that collision, but barely. It reaches intergalactic space while the Milky Way is still a distinct galaxy before the chaos of the merger. And what about humanity during this 428 million year journey? If humanity survives at all, which is a big if, we'd be transformed beyond recognition. Consider that modern humans, Homo sapiens, have only existed for about 300,000 years. That's less than 0.1% of 428 million years. In 428 million years, evolution would have countless opportunities to reshape us. If we stayed on Earth, we'd adapt to changing environmental conditions. As the sun brightens, as temperatures rise, we'd either evolve heat tolerance or go extinct. Assuming we spread to other worlds, which seems likely, if we survive millions of years, we'd split into multiple species. Populations adapting to different planets with different gravity, different atmospheres, different day lengths would diverge. After millions of years of separate evolution, they'd no longer be able to interbreed. They'd be different species. After hundreds of millions of years, they'd be as different from each other as we are from fish. Maybe more. Or maybe we merge with our technology. Maybe we upload our consciousness into machines. Maybe we become something post-human, post-biological, no longer evolved through natural selection, but through deliberate self-modification. Or maybe we go extinct. 99% of all species that have ever existed on Earth are now extinct. Extinction is the norm. Survival for hundreds of millions of years is extraordinary. The horseshoe crab has remained relatively unchanged for about 450 million years, but it's an outlier. Most species last a few million years at most before either going extinct or evolving into something else. Mammals, as a class, have been around for about 200 million years. Primates for about 55 million years. The genus Homo for about 2 to 3 million years. Homo sapiens for 300,000 years. Modern civilization for about 10,000 years. Industrial civilization for about 200 years. The idea that something recognizably human, let alone something recognizably modern civilization, would persist for 428 million years is almost laughable. We'd be gone, transformed, or so changed that the connection to 21st century humans would be historical curiosity at best. Let's also consider what it would take to actually monitor this mission. Somebody has to care. Somebody has to maintain institutional memory across nearly 500 million years. That means records. Physical records, because electronic storage degrades. But physical records also degrade. Paper lasts maybe a few hundred years in good conditions. Stone inscriptions last longer, but they erode. The Rosetta Stone is about 2,200 years old, and it's still readable, but it's also been weathered and damaged. In 428 million years, any stone monument would be worn to nothing by wind, rain, and geological processes. The continents would be in different positions. Plate tectonics moves continents at a few centimeters per year. Over 428 million years, that's thousands of miles. The geography of Earth would be completely different. Mountain ranges would rise and erode away. Oceans would open and close. Nothing would be where it is now. And that's assuming Earth is still habitable, which it won't be for the last few 100 million years of the spacecraft's journey. So maintaining records on Earth won't work. Maybe we keep records on multiple worlds. Maybe we develop some form of cultural continuity that spans worlds and species. Maybe we build monuments in space, artificial structures, orbiting stars, carrying the message that a spacecraft was launched 428 million years ago, and it's still out there, still traveling, still carrying our mark into the void. But even that requires a level of coordination and care that seems implausible over such timescales. Civilizations rise and fall. Empires last a few centuries at most. The longest-lasting continuous civilizations, like Egypt or China, have histories of a few thousand years. And even they went through periods of collapse and reorganization. The idea of maintaining a single continuous project, a single thread of purpose, across 428 million years, seems impossible. More likely, the spacecraft is launched, it departs, and within a few thousand years, people forget about it. It becomes a historical footnote. Then, even the footnote is forgotten. Records are lost. Languages change so much that old records become unreadable. Civilizations collapse and new ones rise, unaware of what came before. After 1,000,000 years, nobody remembers. The spacecraft is out there, dead, coasting through the galaxy, and nobody knows or cares. It becomes the ultimate message in a bottle, except there's no one to find it, no one to read it, just an artifact drifting through eternity. And we're still being generous with our estimates. We assumed the dark matter halo extends to 300,000 light-years. Some estimates put it farther, perhaps 600,000 light-years or even 1,000,000 light-years. If the halo extends to 1,000,000 light-years, our travel time more than triples. At Parker Solar Probe speeds, escape would take over 1.5 billion years. 1.5 billion years ago, Earth had only single-celled life. Multicellular organisms hadn't evolved yet. The most complex life on the planet was bacteria and algae. Everything that came after, plants, animals, fungi, all of it evolved in less time than this spacecraft would need to escape the galaxy. There's also the question of direction. We've been assuming we're traveling straight up out of the galactic disk, perpendicular to the plane. This is the shortest path to leave the disk itself. But if you're trying to escape the gravitational influence of the entire galaxy, including the halo, the shortest path might be different. The halo is roughly spherical, so it might not matter much which direction you travel. But the galaxy is also moving through space, part of the local group of galaxies, and the local group is falling toward the Virgo supercluster. All of this affects the effective escape velocity depending on which direction you're traveling. If you're traveling in the direction the galaxy is moving through space, you get a boost. If you're traveling against that motion, you have to fight it. These are small effects compared to the overall escape velocity, but they complicate the calculation. And here's something we haven't even addressed yet. We've been talking about leaving the Milky Way as if it's a static object. But the galaxy is dynamic. It's rotating. Its shape is changing slowly over time, and in about 4 billion years, it's going to collide with Andromeda. If you launched a spacecraft today intending to escape the Milky Way, and it took hundreds of millions of years to get beyond the halo, by the time it escaped, the galaxy would have changed. The collision with Andromeda would scramble everything. Stars from both galaxies would mix. The gravitational field would be completely different. The very definition of what constitutes the Milky Way would become unclear. Are you escaping the Milky Way, or the merged galaxy, or what? The mission objective becomes meaningless on these timescales. Let's consider an even more exotic propulsion method. What if we built a spacecraft powered by antimatter? Antimatter is the most energy-dense fuel theoretically possible. When matter and antimatter meet, they annihilate completely, converting 100% of their mass into energy. According to Einstein's equation, E equals mc squared. This is far more efficient than nuclear fusion, which converts less than 1% of mass into energy. An antimatter rocket could theoretically reach significant fractions of light speed. Let's say we could build one that reaches 50% of light speed. At that speed, escaping the Milky Way's halo would take around 548,000 years. Still incredibly long, but at least it's under 1,000,000 years. In 548,000 years, humanity could plausibly maintain some form of continuity. Civilizations have existed for only about 10,000 years, but 548,000 years is imaginable in a way that 428 million is not. But here's the problem. We have no idea how to build an antimatter rocket. Antimatter exists. We've created tiny amounts in particle accelerators, but it's phenomenally difficult to produce and store. Creating a single gram of antimatter would require more energy than humanity produces in a year, and you'd need tons of it to fuel a spacecraft. Storing it is another nightmare because antimatter annihilates instantly upon contact with normal matter. You'd need magnetic containment systems that could operate perfectly for hundreds of thousands of years. Any failure, any tiny leak, and the antimatter touches the container and explodes with the force of multiple nuclear weapons. So, while antimatter propulsion is theoretically possible, it's so far beyond our current capabilities that we might as well be talking about magic. What about theoretical concepts from physics that might allow faster-than-light travel? Warp drives, wormholes, concepts like that? These appear frequently in science fiction, and some have a basis in actual physics. But the reality is far more complicated than the stories suggest. The Alcubierre drive is a solution to Einstein's field equations that would allow a spacecraft to effectively travel faster than light by contracting space in front of it and expanding space behind it. The spacecraft would sit in a bubble of normal space, and the bubble itself would move through space-time faster than light. On paper, this doesn't violate relativity because the spacecraft itself isn't moving faster than light through space. Space itself is moving, carrying the spacecraft along. It's like surfing a wave. The surfer isn't moving faster than the wave, they're riding it. In the Alcubierre drive, you create a wave in space-time and ride it. The math works out, at least in general relativity. Miguel Alcubierre published this solution in 1994, and it caused excitement because it showed that faster-than-light travel might not be completely impossible. But there are problems. Big problems. The Alcubierre drive requires exotic matter with negative energy density. What does that mean? Normal matter has positive energy density. A kilogram of matter has mass, which is equivalent to energy through E equals mc squared. Exotic matter would have negative energy density. It would have negative mass, in some sense. No such matter is known to exist. We've never detected anything with negative energy density. Some physicists think it can't exist, that quantum mechanics forbids it through various theorems and constraints. The Casimir effect produces something like negative energy density in a very limited sense, but it's not clear if this can be harnessed for an Alcubierre drive. And even if exotic matter exists, you'd need enormous amounts of it. Early calculations by Alcubierre suggested you'd need more mass energy than exists in the entire observable universe. That's not just impractical, it's absurd. Later refinements by other physicists reduced that requirement. By tweaking the shape of the warp bubble, you can reduce the amount of exotic matter needed. Some calculations suggest you might be able to do it with the mass-energy equivalent of Jupiter. Still absurdly large. But at least it's not larger than the universe. But there's still the problem of how you create this exotic matter in the first place, and how you shape it into the precise configuration needed for a warp bubble, and how you control the bubble once it's formed. The mathematics of the Alcubierre drive don't tell you how to actually build one. They just show that if you had the right distribution of exotic matter, a warp bubble would form. It's like showing that a car is physically possible without explaining how to build an engine. And there are causality problems. If you can travel faster than light, even in this indirect way, you can potentially create time loops. Sending a signal faster than light is equivalent to sending it backward in time from certain reference frames. This leads to paradoxes. You could send a message to yourself in the past. You could potentially violate causality, creating grandfather paradoxes and other logical contradictions. Many physicists think the universe simply won't allow this. There must be some mechanism that prevents faster-than-light travel, even using tricks like warp drives, because allowing it would violate causality. What that mechanism is, we don't know. But the smart money is on warp drives being impossible, not for engineering reasons, but for fundamental physical reasons. Wormholes face similar issues. A wormhole is a hypothetical tunnel through space-time connecting two distant points. In theory, you could connect two distant locations in space with a tunnel through higher dimensional space-time. Enter one end of the wormhole, travel a short distance through the tunnel, emerge from the other end far away. The concept comes from general relativity. Einstein's equations allow for solutions that include wormholes. The simplest example is the Schwarzschild wormhole, derived from the equations for a non-rotating black hole. But there's a problem. The Schwarzschild wormhole connects two regions of space-time, but the connection pinches off so quickly that nothing, not even light, can traverse it before it closes. You'd need to travel faster than light to get through, which defeats the purpose. To keep a wormhole open, you'd need to thread it with exotic matter, the same stuff the Alcubierre drive needs. Matter with negative energy density that would counteract the natural tendency of the wormhole throat to pinch shut. And you'd need a lot of it, distributed precisely throughout the wormhole throat. Again, we have no idea how to create exotic matter or if it even exists. And even if you could build a wormhole, there's another problem. You can't use a wormhole to go anywhere you haven't already been. Here's why. To connect two distant points with a wormhole, you need to have wormhole mouths at both locations. You can't just create a wormhole to a distant galaxy from your starting location. You'd need to physically transport one wormhole mouth to the distant galaxy using slower-than-light travel. Then, once it's there, you could use the wormhole for rapid transit. But the initial journey to emplace the wormhole still requires conventional travel. So wormholes don't help you escape the galaxy unless you've already escaped using slower methods and brought a wormhole mouth back. They're useful for creating a permanent shortcut, but they don't help you make the first trip. There are also causality problems with wormholes. If you can make a wormhole, you might be able to convert it into a time machine under certain conditions. This again leads to paradoxes. Many physicists think there's some kind of chronology protection mechanism in physics that prevents time machines from forming. What that mechanism is remains unclear, but it probably also prevents traversable wormholes from existing. What about other speculative ideas? Some science fiction invokes hyperspace, an alternate dimension where the laws of physics are different and faster-than-light travel is possible. But there's no evidence for hyperspace. It's pure speculation, not based on any known physics. Other ideas include quantum tunneling on a macroscopic scale. Quantum particles can tunnel through barriers they shouldn't be able to cross classically. Maybe a spacecraft could quantum tunnel from here to a distant location. The problem is that quantum tunneling probability drops exponentially with the size of the object and the distance. For something as large as a spacecraft, tunneling even a millimeter is so improbable that it would never happen. Tunneling across light years is completely impossible. The probability is so close to zero that it might as well be exactly zero. Some theories of quantum gravity suggest space-time might have a foam-like structure at very small scales, the Planck scale. Maybe you could exploit this structure to create shortcuts through space. Again, pure speculation. We don't have a working theory of quantum gravity yet. String theory, loop, quantum gravity, and other approaches are still being developed. They might predict exotic phenomena, or they might not. Until we have a complete theory and experimental tests, we can't say. The reality is that faster-than-light travel, in any form, probably violates fundamental physics. Not just engineering limits, but limits imposed by the structure of space-time itself. Relativity has been tested extensively. Every prediction has been confirmed. Time dilation, length contraction, mass-energy equivalence, gravitational lensing, gravitational waves, black holes, everything. Relativity works. And relativity says nothing with mass can reach light speed, let alone exceed it. You can invent scenarios that try to circumvent this by manipulating space-time itself rather than moving through it. But these scenarios always require exotic matter or other things we have no evidence for. And they often lead to causality violations, which suggests they're forbidden by deeper principles we don't yet fully understand. So the honest assessment is that faster-than-light travel is probably impossible. Not just impractical, but actually forbidden by physics. We might be wrong. Physics has surprised us before. But based on what we know now, you can't escape the Milky Way quickly. You're stuck with slower-than-light travel and all the absurd timescales that entails. The conclusion is unavoidable. Leaving the Milky Way is not something humanity can do with foreseeable technology. It's not even something humanity can do with wildly optimistic extrapolations of future technology. It's something that would require either faster-than-light travel, which may be physically impossible, or generation ships traveling for hundreds of thousands or millions of years, which is practically impossible. We are, for all intents and purposes, trapped in this galaxy. Not by politics or lack of funding or engineering challenges, but by the fundamental nature of space and time. But maybe that's not such a bad thing. The Milky Way is enormous. It contains somewhere between 200 and 400 billion stars. Let's use a conservative estimate and say 200 billion. That's 200 billion separate star systems. Many of those stars have planets. Data from the Kepler Space Telescope and other planet-hunting missions suggests that planets are extremely common. Most stars have at least one planet. Many have multiple planets. The number of planets in the Milky Way is probably in the trillions. Not all of these planets are habitable, of course. Most are too hot, too cold, too large, too small, or otherwise unsuitable for life as we know it. But even if only a tiny fraction are habitable, we're still talking about billions of potentially Earth-like worlds. Recent estimates suggest there might be 40 billion Earth-sized planets in the habitable zones of their stars within the Milky Way. 40 billion worlds where liquid water could exist on the surface. 40 billion places where life might emerge, where intelligence might evolve, where civilizations might rise, or where human colonists might build new homes. If humanity ever develops the technology for interstellar travel, even slow interstellar travel, we could spread throughout the galaxy. We could colonize 1,000,000 worlds, 1 billion worlds, without ever needing to leave the Milky Way. And we wouldn't need faster-than-light travel to do it. Just patience and incremental expansion. The nearest star to our Sun, Proxima Centauri, is only 4.24 light-years away. At 10% of light speed, that's a 42-year journey. Long, yes, but achievable within a human lifetime, especially with suspended animation or generation ship concepts. A generation ship is a spacecraft designed to support a crew for multiple generations. The people who launch the ship wouldn't be the ones who arrive. Their children or grandchildren or great-grandchildren would complete the journey. It's not a new idea. The concept goes back to the early 20th century, proposed by scientists and science fiction writers trying to envision realistic interstellar travel. For a 42-year journey to Proxima Centauri, you wouldn't even need multiple generations if you had working suspended animation. Put the crew in some kind of hibernation, wake them up when they arrive. Even without that, 42 years is manageable. People live longer than that. You could launch young and arrive old, but still alive. If we could reach 20% of light speed, which might be achievable with advanced fusion rockets or laser-pushed light sails, the journey to Proxima Centauri drops to 21 years. 1 generation. Half a human lifetime. And once you reach Proxima Centauri, you can establish a base there. Mine resources from the asteroids and outer planets. Build ships. Reach out to the next nearest stars. Alpha Centauri A and B, the binary companions to Proxima, are right there, 4.37 light-years from Earth. Barnard's star is 6 light-years away. Wolf 359 is 7.9 light-years away. Sirius, the brightest star in our sky, is 8.6 light-years away. All of these are reachable within decades, at 10 to 20% of light speed. Slowly, incrementally, you build a network of colonies spreading outward from Earth. Each colony establishes infrastructure, builds ships, reaches out to nearby stars. It's exponential growth, limited only by the speed of your ships and the availability of habitable worlds. Computer simulations of this process, modeling how a spacefaring civilization might spread through the galaxy, show that you could colonize a significant portion of the Milky Way in a few million years. Not the whole galaxy, because the galaxy is too big and expansion wouldn't be uniform. Some directions would have more habitable worlds, faster expansion. Other directions would hit dead zones with few stars or hostile environments, slower expansion. But tens of thousands or even hundreds of thousands of star systems could be reached in 1,000,000 years. And remember, 1,000,000 years is short compared to the age of the galaxy or the lifespan of stars. The Sun has another 5 billion years of stable life left. A 1,000,000-year expansion phase is less than 0.02% of that time. It's nothing on cosmic timescales. And what's out there to colonize? We've discovered thousands of exoplanets in the past few decades. Most were found by the transit method, watching for the tiny dip in a star's brightness when a planet crosses in front of it. The Kepler Space Telescope alone discovered over 2,600 confirmed exoplanets. TESS, the Transiting Exoplanet Survey satellite is finding thousands more. These missions have revealed that planetary systems are incredibly diverse. Hot Jupiters, gas giants, orbiting closer to their stars than Mercury orbits the Sun, completing an orbit in just a few days. Super-Earths, rocky planets larger than Earth, some in their star's habitable zone. Mini-Neptunes, worlds slightly larger than Earth, with thick atmospheres of hydrogen and helium. Circumbinary planets, orbiting binary star systems, like Tatooine from Star Wars, but real. Planets around red dwarf stars, the most common type of star in the galaxy. Planets around sun-like stars. Even planets around dead stars, white dwarfs, and neutron stars, somehow surviving the death of their parent star. Some of these exoplanets are fascinating from a habitability perspective. Kepler 452b, a planet orbiting a sun-like star in its habitable zone, about 60% larger than Earth. Proxima Centauri b, orbiting our nearest stellar neighbor, possibly habitable, though it might be tidally locked. TRAPPIST 1e, one of 7 Earth-sized planets orbiting an ultra-cool red dwarf star, several of them in the habitable zone. LHS 1140b, a dense super-Earth orbiting a red dwarf, possibly with a thick atmosphere. We don't know if any of these planets actually have life. We haven't detected biosignatures yet, but they're proof that Earth-like worlds exist. And if a tiny sample of nearby stars yields multiple potentially habitable planets, the galaxy as a whole must contain billions of them. Colonizing other worlds wouldn't be easy. Even if you find a planet in the habitable zone with liquid water and a breathable atmosphere, it won't be exactly like Earth. The gravity might be different, higher or lower, depending on the planet's mass and radius. Humans could probably adapt to variations of plus or minus 50%. But beyond that, health problems develop. Too low, and your bones weaken, muscles atrophy. Too high, and your heart has to work too hard. Joints wear out, movement becomes exhausting. The day length might be different. If the planet is tidally locked, one side always faces the star, one side always faces away. The day side would be hot, the night side cold. Life, if it exists at all, would cluster in the twilight zones between. Even if the planet rotates, the day length might be very different from Earth's 24 hours. This affects circadian rhythms, sleep cycles, everything biological. Humans might adapt over generations, but it would be difficult. The atmosphere might be breathable, but still different from Earth's. Maybe slightly more oxygen, which would increase fire risk and possibly affect long-term health. Or slightly less, requiring supplemental oxygen for strenuous activity. Maybe different atmospheric pressure, requiring acclimatization. And there's the biosphere. If the planet has native life, that life evolved independently from Earth life. Different biochemistry, different proteins, different sugars. Earth life might not be able to digest native food. Native microbes might not be able to infect humans, but they might still cause allergic reactions or other immune responses. Terraforming might be necessary, or at least significant adaptation. Building enclosed habitats. Growing Earth crops in greenhouses. Slowly modifying the environment to be more Earth-like. Or modifying humans to be more suited to the new world. Genetic engineering to tolerate higher or lower gravity, different day lengths, different atmospheric compositions. Over generations, human populations on different worlds would diverge. They'd adapt to their local conditions. Eventually, they might diverge enough to become separate species. A fascinating thought. Humanity spreading to 1,000 worlds, evolving into 1,000 different but related species, all descendants of Earth, all bearing the mark of our origin. And it's not just habitable planets that offer opportunities. Moons might be habitable. Jupiter's moon Europa has a subsurface ocean beneath its icy crust. Saturn's moon Enceladus has similar ocean beneath ice. These oceans might harbor life, though they're probably cold and dark, relying on chemical energy rather than sunlight. For colonization, you'd need to drill through the ice or melt access tunnels. Build habitats in the ocean or in the ice shell. It's harder than colonizing a terrestrial planet, but it's possible. Titan, Saturn's largest moon, has a thick atmosphere and lakes of liquid methane on its surface. Not habitable for humans directly, but you could build enclosed habitats. The resources are there, hydrocarbons everywhere, water ice beneath the surface. Asteroids and comets could be mined for resources. Metals, water, carbon, nitrogen, everything needed to build habitats and spacecraft. O'Neill cylinders, rotating space habitats that generate artificial gravity through spin, could house millions of people. Build them in orbit around stars, or in the space between stars, using resources from asteroids. You wouldn't even need planets. Just raw materials and energy. The possibilities are vast. The Milky Way contains resources beyond imagining. Entire worlds waiting to be explored. Elements forged in dying stars scattered through space. Energy from billions of stars. Everything needed for civilization to grow, expand, and thrive for millions of years. There's also something poetic about being bound to the Milky Way. This is our home on the largest scale. Our solar system formed from material that was forged in stars that lived and died within this galaxy. The heavy elements in our bodies, the carbon, oxygen, iron, calcium, all of it was created in stellar furnaces and scattered by supernovae, all within the Milky Way. We are made of the galaxy in a very literal sense. The atoms in your hand right now were once part of stars that orbited the galactic center billions of years ago. Perhaps some of those atoms were part of planets that no longer exist, worlds that were destroyed when their star died. We're connected to this galaxy by more than just gravity. We're connected by composition, by history, by origin. The Milky Way created us. It's fitting that we remain bound to it. And the galaxy itself is beautiful. On a dark night, far from city lights, you can see the Milky Way band stretching across the sky. That soft glow is the combined light of billions of stars, most of them too faint to see individually. You're looking at the galaxy from the inside, seeing the disk edge on. Every star you can see with your naked eye is part of the Milky Way. Every constellation, every bright point in the night sky, they're all our galactic neighbors. The farthest star visible to the naked eye is V762, Cassiopeia, roughly 16,000 light-years away. Still well within the Milky Way. Still part of our home galaxy. Andromeda, the nearest large galaxy, is visible as a faint smudge to the naked eye, but it's 2.5 million light-years away. Everything else you see, all the individual stars, are nearby on cosmic scales, all part of this gravitational structure we call the Milky Way. Let's return to our original question with a more complete answer. If we left today, how long would it actually take to escape the Milky Way? Using our best current technology, the Parker Solar Probe's speed of 119 miles per second, it would take approximately 428 million years. Using optimistic near-future technology, like nuclear pulse propulsion reaching 10% of light speed, it would take about 2.74 million years. Using wildly speculative far-future technology, like antimatter rockets, reaching 50% of light speed, it would take around 548,000 years. All of these timescales are so long that the mission becomes meaningless. Spacecraft can't survive that long. Civilizations can't maintain continuity that long. Evolution would transform humanity beyond recognition. The galaxy itself would change substantially. And this assumes we solve impossible engineering challenges and develop technologies that may not even be possible. The only scenarios where escaping the Milky Way becomes feasible involve faster-than-light travel, warp drives, wormholes, something that breaks the light speed barrier. But these technologies may be physically impossible. They certainly violate our current understanding of physics or require exotic matter that may not exist. So the honest answer is that we can't escape the Milky Way. Not now, not in the foreseeable future, probably not ever. The distances are too vast. The time scales too long. The energy requirements too extreme. The galaxy is our home, and barring revolutionary discoveries in physics that completely overturn our understanding of space-time, it's where humanity will remain. There's a lesson here about scale. We're used to thinking of space as big, but empty and traversable. The moon is far, but we've been there. Mars is farther, but we're planning missions. Even the outer solar system seems reachable with enough time and resources. But the galaxy is different. The galaxy is so large that even light, the fastest thing in the universe, takes 100,000 years to cross it. Our fastest spacecraft would take billions of years. These aren't engineering challenges. They're fundamental limits imposed by physics. The speed of light is a cosmic speed limit, and the distances involved are so enormous that even traveling at that limit wouldn't help on any human timescale. This is humbling. We live in an age where technology has made the world feel small. You can fly to the other side of Earth in less than a day. You can communicate instantly with someone on the opposite side of the planet. We've sent machines to every planet in our solar system. We've landed rovers on Mars and flown a helicopter in its thin atmosphere. It's easy to feel like nothing is impossible, like any destination can be reached with enough determination and clever engineering. But the galaxy reminds us that we're still tiny. We're confined to a small region of space near one ordinary star. We've barely left our own planet. The farthest human-made object, Voyager 1, launched in 1977, has traveled about 14.5 billion miles from Earth. That sounds like a lot until you realize it's only 0.002 light-years. It hasn't even left the solar system's influence completely. In 40,000 years, Voyager 1 will pass within 1.6 light-years of a star called Gliese 445. That will be the first time any human-made object comes close to another star. 40,000 years for a close pass, not even a visit, just a flyby. And that's to reach a nearby star, not to escape the galaxy. Yet even within these constraints, there's wonder. The Milky Way contains multitudes, hundreds of billions of stars, each one potentially surrounded by planets, nebulae, where new stars are being born, supernova remnants, where old stars died. Black holes, neutron stars, white dwarfs, every exotic object physics allows. Globular clusters containing millions of ancient stars. Open clusters of young hot stars. Molecular clouds spanning hundreds of light years. The galactic center with its supermassive black hole, Sagittarius A, weighing 4 million times what the Sun weighs. All of this is within our galaxy. All of this is, in principle, reachable even with slower-than-light travel. If humanity survives, if we develop interstellar travel, we could spend millions of years exploring our own galaxy and never run out of places to go. Every star is a destination. Every planet is a potential new world. We don't need to escape the Milky Way. We need to explore what's already here. And maybe someday, far in the future, long after humans have spread to 1,000 worlds, long after we've evolved into forms we wouldn't recognize today, maybe our distant descendants will develop technologies we can't imagine. Maybe they'll find a way to warp space, or open wormholes, or manipulate dimensions we don't even know exist. Maybe for them, leaving the galaxy will be as routine as flying to another continent is for us. But that's speculation bordering on fantasy. For now, for the civilization we are today, escaping the Milky Way is impossible. The galaxy is our home. It's where we evolved. It's where we'll remain. And that's okay. There's enough here to keep us busy for a very long time. The Milky Way is rushing through space at 1.3 million miles per hour, falling toward the Great Attractor, a gravitational anomaly hundreds of millions of light years away. It's rotating, completing one rotation every 225 million years. It's alive with activity, stars being born, stars dying, black holes feeding, gas clouds colliding. And we're part of it. We're riding along on this vast cosmic structure, orbiting the center, moving through space at incredible speeds, bound by gravity to hundreds of billions of other stars. We can't escape it, but we can explore it. We can understand it. We can appreciate that we exist within something so much larger than ourselves. Think about what you're part of right now. You're on Earth, a planet orbiting the Sun. The Sun is orbiting the galactic center at 140 miles per second. You're moving through space at that speed right now, carried along by the Sun's motion. In the time it took you to watch this, you've traveled thousands of miles through the galaxy without even noticing. You'll complete a full orbit in 225 million years. The Sun has been around for about 20 of those orbits. It has maybe 40 more orbits left before it runs out of fuel, expands into a red giant, and begins dying. And throughout all of that, through the Sun's entire life, it will remain bound to the Milky Way. It will never escape, and neither will we. Unless something truly revolutionary happens, unless physics has surprises we haven't discovered yet, humanity's future is in this galaxy. We might spread to other stars. We might build habitats in space, artificial worlds that house billions. We might become a multi-planet, multi-star species. But we'll do it all here, within the Milky Way's gravitational embrace. The galaxy that gave birth to our Sun. The galaxy that provided the elements for our planet. The galaxy that made life possible. Our home, in the deepest sense. This story we've told tonight isn't one of adventure and exploration across the universe. It's a story of limits, of boundaries we can't cross, of distances so vast they make human ambition seem almost laughable. But it's also a story of acceptance, We don't need to escape to find meaning. We don't need to conquer the universe to matter. We exist in this moment, on this world, in this galaxy. And that's enough. The Milky Way is enough. Thanks for staying with me through this journey, across impossible distances and unimaginable timescales. The dream of escaping the galaxy might be forever out of reach, but understanding why teaches us something profound about the universe and our place in it. We're bound to this galaxy by gravity, by the nature of space-time, by the fundamental limits of physics. And maybe that's exactly where we're meant to be. There's something profound in this realization. We spend so much time looking outward, dreaming of distant galaxies, imagining futures among the stars of other cosmic structures. But in doing so, we sometimes forget the incredible privilege of existing here, now, in this particular galaxy, at this particular time. The Milky Way is approximately 13.6 billion years old. The universe itself is about 13.8 billion years old. Our galaxy formed when the universe was young, when the first generation of stars was just dying out, when heavy elements were first being scattered into space. The Sun and our solar system formed 4.6 billion years ago, when the galaxy was already ancient. We're latecomers to this story. The galaxy had been here for billions of years before the Sun ignited. Stars had been born and gone countless times before our Sun even existed. Supernovae had enriched the interstellar medium with the elements that would eventually form Earth and everything on it. We exist because of billions of years of stellar evolution, cosmic recycling, the gradual building up of complexity from simple hydrogen and helium to the rich chemistry of life. And all of that happened here, in the Milky Way. Our origin story is written in the stars of this galaxy. Every atom in your body was forged in stars that lived and went within these spiral arms. The calcium in your bones came from supernovae. The iron in your blood came from dying stars. The oxygen you breathe, the carbon that forms the basis of all organic molecules, all of it was created in stellar furnaces and scattered into space by stellar winds and supernova explosions. We are literally made of stardust, as Carl Sagan famously said. But more specifically, we're made of Milky Way stardust. This galaxy's stardust. The atoms that make you have been part of this galaxy for billions of years. They've orbited the galactic center countless times. They've been part of different stars, different planets, different molecular clouds. And now, they're temporarily organized into the pattern that is you. Eventually, those atoms will return to the galaxy. Your body will break down, decay, return to the Earth, or be scattered into space depending on how far into the future we're talking. The atoms will be recycled. Maybe some will end up in future stars. Maybe some will become part of planets yet to form. The cycle continues. This is the perspective that really matters. Not whether we can escape the galaxy, but understanding that we're part of it in a fundamental way. The galaxy isn't a prison. It's not a cage keeping us trapped. It's our origin, our home, the structure that made our existence possible. Being bound to it by gravity is no different than being bound to Earth by Earth's gravity, or bound to the Sun by the Sun's gravity. It's just the natural state of existence in a universe governed by the laws of physics. And there's beauty in that limitation. Constraints drive creativity. Having infinite possibilities can be paralyzing. But having a finite domain, a bounded space to explore, gives focus. The Milky Way is vast enough to contain wonders beyond imagining, but small enough that we can conceive of exploring significant portions of it. It's the right scale for human ambition. If the entire universe were easily accessible, if we could hop between galaxies at will, would individual galaxies matter? Would we care about any particular star system, any particular world? Or would it all become homogeneous, interchangeable, one galaxy much like another? But because we're bound here, because this galaxy is our domain, every star becomes precious. Every world becomes significant. The constraints give meaning. They force us to look closely at what's here, rather than always reaching for what's beyond. This is true on smaller scales too. Earth is our home world. We can't easily leave it. Even reaching orbit requires enormous energy and engineering. Traveling to other planets in our solar system takes months or years. These constraints shape how we think about Earth. Because leaving is hard. Because we can't simply move to another planet when we damage this one, we have to care about Earth. We have to protect it, preserve it, understand our dependence on it. The same will be true as we spread to other worlds in the galaxy. Each world will be precious because reaching the next one requires years or decades of travel. You can't casually move between star systems the way you can move between cities. Every world becomes a long-term commitment. This creates responsibility, investment, a reason to care deeply about each place rather than treating them as disposable stepping stones. Maybe that's how it should be. The laws of physics create natural boundaries. The speed of light separates regions of space. The expansion of the universe creates horizons beyond which we can never reach. Dark energy ensures that distant galaxies will eventually become unreachable, no matter how long we wait or how fast we travel. The universe is compartmentalized, divided into domains. Each galaxy is its own realm, each one isolated from the others on timescales shorter than cosmic evolution. And within each realm, life can emerge, evolve, potentially develop intelligence and civilization. Each one following its own path. Some might develop space travel. Some might reach for the stars. Some might remain planet-bound for the entire duration of their existence. All of these possibilities play out independently in billions of separate galaxies scattered through the universe. And perhaps that's the richness of creation. Not one story, but countless separate stories, each one unique, each one playing out in its own isolated domain. We're living one of those stories. Our story is the Milky Way's story, and it's still being written. So when you look up at the night sky, when you see that band of light stretching from horizon to horizon, remember what you're looking at. You're seeing home. Not just Earth, not just the solar system, but the entire vast structure that contains us. Hundreds of billions of stars, trillions of planets, more worlds than we could ever explore, more wonders than we could ever catalogue, all bound together by gravity into this single magnificent structure, the Milky Way, our galaxy, the only one we'll ever need.